we want to look at another way of representing a complex number. This is called the polar form. Now, to explain it, we must look at what we've been representing so far is called the rectangular form. So that's a plus bi. So a plus bi, you can think of it goes across a and it goes up b. And if you think of a rectangular, that's where the rectangular form of a complex number comes from. So we're quite used to that at this point. Now there's another way to represent that, is if we take a look at the distance the complex number is from the origin, that distance, and we give that the letter r, or there's another way to represent it. You can represent it as the name of the complex number with two lines across it, and it's called the modulus. Or some people call it the radius. And you can think of the radius as how far that point is out around the circle. Now, to specify that particular complex number, you must give it an angle. So in this case, we have an angle here with the positive x-axis, and we give that angle a name that's called the argument. So if we represent these two numbers, will give us another way to show the to represent a complex number. So how do we do that? Well, if we remove that for a second and just look now at this triangle here. So if we just put this down here and this across here, if we asked what is, let's say in this case, what is this side? We call that B, and let's call that A. So what is B? So in this case, B, I want you to realize, is that B, so let's say the sine of the angle. So let's take the sine of theta is B over R. So B then, B is R sine theta. And then A, if we try to find A, that's the cos of theta, is A over R. So A then is R cos theta. So to represent it in polar form, then what you would do is you would have R cos theta plus I sine theta, because so to represent it in polar form, then you can go with the modulus, which is R times sine. Then to represent it in polar form, what you would do is you want A, in this case A plus BI. So A plus BI, if we write it out this way, is A is R cos theta, plus, and B in this case is R sine theta, and then there's an I, of course, there with the B. So what we could do is take out the R, so we would have R cos theta plus I sine of theta. And that is called the polar form of a complex number. And when you think polar form, I want you to think of a radar. So think of circles like this, and to specify it in polar form, you could, this is, let's say the complex number is the distance out by the angle made. So that's polar form. And it's very useful, and the reason it's very useful is you can use it for multiplying complex numbers. It's an easier way to visualize it, and it's also used when you get complex numbers to certain powers. So how do we then actually mathematically get that? Well, what we need to do is first we need to find the modulus. So if we look at the modulus now, so how do you get the distance between 2 points? Well, of course, we can use the distance formula, x2 minus x1, all to be squared, plus y2 minus y1, all to be squared. And in this case, if we take the origin, which is one of our points, and we're going to use the example we have here is 2 plus 3i. Well, let's use the, well, actually what we'll do is we'll use a and b B for the A and B to be the other point. So we just in this example, let's take A and B to be our point there. So it's 0, 0 is one point and A, B is the other. So what we're going to do is we will look at it. If we take that to be x1, y1, and A, B, that would be y2, x2, y2. Restart now, just wait for my restart. Okay, so we can use the so what we'll do is we'll use our two points in this case is 0, 0, which is the origin, and the other point is A, B. So if we have this is x1, y1 and x2, y2, and we plug that into the formula for the distance, we will get the square root of, and we're going to get A minus 0 all to be squared plus B minus 0 all to be squared. So the modulus ends up being the square root of A squared plus B squared. So the modulus for every complex number is the square root of A squared plus B squared. So for this particular example, 2 plus 3i, what we could do is look at the modulus of the modulus of z1 in this case, which we have, is the square root of 2 squared plus 3 squared. And that is the square root of 4 plus 9, which is the square root of 13. Just give an example there of finding the modulus. Now, how do we find the argument? So the argument in this case, if we go back to the diagram, if you can see that the tan of theta, if we use, because we have the opposite and adjacent, so the tan, I might use just a different color for that there. If we use the tan of theta is equal to B over A. So to find theta is the inverse tan of B over A. So in our example, we'll use 2 and 3 in this case. So to find the argument, to find theta in this case is the inverse tan of, in this case, it's 2, 2, 3. So it'll be 3 over 2. And you can use your calculator for that. Mine has disappeared. Where's it gone? And you can use your calculator for that. So you can use your calculator to get the inverse tan of 1.5, and you will find that that comes out to be 0.98. Oh, to get the argument for a complex number, what we need to do is we need to get the tan of theta. So the tan of theta is B over A. In this case, you can see it's opposite over adjacent. So theta is equal to the inverse tan of B over A. Now, theta in the polar form is represented as radians. So we'll go just kind of a little recap on radians, just so we understand. Just a recap on radians. So if you take the radius of a circle, and you take that length, let's call it R, and you put that onto the arc of the circle. So that length onto the circle, the angle that makes is 1 radian. So you can see that it's 1 radian, it's about 52 degrees. So if you move that along, you can see that in 180 degrees there are pi radians. So that's 3.14 radians. In a full circle then, if you took a full circle, that would be double that. So that would be 6.28 radians. So just a quick recap on radians. So now that we understand radians, let's get the argument for this particular complex number, 2 plus 3i. So theta in this case is the inverse tan of 3 over 2, and you can use your calculator to get that, and in radians you'll find that to be 0.98. So that is the argument, and we have the modulus. So to represent it in polar form, then what we're going to do is we're going to put the modulus first, so the square root of 13, and then it is cos of the argument, and the argument in this case is 0.98, and then it's plus I sine of the argument. So that is 2 plus 3i in polar form. So I just wanted to show you there are other ways to represent it in polar form. These are all polar forms. So if we look at the different ways of representing things in polar forms, you have what we were talking about here, r cos of the argument, so theta, plus I sine of theta. And that is the polar form, the trigonometric polar form. There's another way that engineers use to represent it is r, what's called cis of the angle. Cis is the cos of theta plus I sine of theta. Engineers also use another way to do it, it's called the mod argument way to represent it, and this is very concise, but it isn't used in leaving cert. So it is just the r, and then you have an angle, and then you put in theta. So in this case you would have, it would be the square root of 13 angle 0.98. So you just have the mod argument. And another way to represent it then is also that it's equal to r e to the I theta. But this brings in the extra confusion that some students might have when you introduce e in these terms. So these are used in engineering, and this one is also used in mathematics, but we don't use it in most. This is the format that we use for the leaving cert. But it's just good to just see the other representations of the polar form of complex numbers. Another thing we might mention is that when you're getting the argument of a complex number, that there are particular values for tan that you should look out for. So if you can see here, we have the unit circle, and we have the values for tan for the different angles. So if you get values like square root of 3 or 1 or 1 over the square root of 3, or negative versions of that, such as over here we'd have minus 1 over the square root of 3. If you get values like that, then you should, in the polar form version, you should take the argument to be able to, if we take the example of minus 1 over square root of 3, you should take the argument to be 5 pi over 6 if the complex number is in that quadrant. If you, let's say, the complex number was in the fourth quadrant, then you would take it to be 11 pi over 6. So you have to look at where the complex number is in the quadrants when you're looking at arguments. So to give you one example there, let's just take the example of, let's say you found that the tan of theta was square root of 3. Well, in that case, what you can say is that theta is pi over 3. So you can use that in the polar form, which would be r times cos of pi over 3 plus I sine of pi over 3. This is a format that they like in leaving cert. They like to have it in terms of radians, not in terms like we had in the earlier, where we had the we found that the theta was equal to 0.9 radians. They like to have it in terms of pi over 3 radians, or 5 pi over 4 radians. But that's not always possible. It's only when you have tans of these values that you can do that.